welcome everybody to Practical Archive Dives with Oxen.ai. Today we're going to be going over the Mamba paper, but actually implementing it in code. So today will be how to train Mamba for the task of question answering. So it's a fun one. My background is actually a lot in the question answering space. I used to work at a startup that was building a competitor to IBM Watson, and then eventually we got acquired into the Watson team. So I've done a lot of just question answering stuff in the past, and it was fun to kind of bring back those roots the past week and try to apply this new architecture, Mamba, to this age-old task of answering questions. So with that said, let's start with a brief overview of what is Mamba. There's been a lot of hype over the past couple weeks about Mamba. It was released back in, well, the start of December. It's like this stuff moves so fast. It was released this month, and it claims 5x faster throughput compared to transformers, and scales linearly with the context length, which is pretty exciting. And today we're going to get to see why those things are important. Last Friday, we went into the details of how the architecture works. So if you want to catch up on that afterwards, we have this whole blog that goes into it. And if you don't want to know about the internals and just want to see how the model performs, this is the one for you. So what are we building? Today, we'll be building a question answering system using Mamba as the backbone, as the base LLM. So at a high level, we'll be able to do things like ask the model, what is the capital of Norway? And hopefully it says Oslo. And these models were pre-trained on a lot of unstructured text data, specifically the pile dataset, and it's encoded into its parameters a lot of this knowledge, and we're going to see how we can extract that out in a question answering system. It's pretty cool because systems like IBM Watson that I worked on in the past had a lot of handcrafted features just to be able to answer Jeopardy questions. So we were doing things like handwriting C++ code to extract all of the nouns and pronouns and verbs and see how they link together. And at the end of the day, Watson was like this one logistic regression on the top of a bunch of hand engineered features. And today, LLMs kind of abstract away all of those features and their parameters. So I'm excited to see how it works on a question answering data set. And I hadn't played with question answering systems in years, so it was kind of fun to dive into how that works. So the Mamba paper should be really well suited for the question answering problem. Processing a large context window of, they claim, up to 1 million in length is a key component of building a QA system. So how can we extract an answer out of a paragraph of text, or even like a large, maybe a book, and the answer is somewhere hidden within the book. But before we get ahead of ourselves, let's just kick around the pre-trained model itself, the raw language model. And all of these models are linked to in this state spaces / Mamba GitHub repository. That was the original author's repository, and they have a bunch of different sizes within there, everywhere from 130 million parameters to 2.8 billion parameters. And I played with a couple of the different sizes. All of them were pre-trained on the pile, and they picked their model dimensions based off of the GPT-3 paper. But in order to see how any of this stuff works, we're going to start with the smallest model. I think it's fun for these practical sessions to see what sort of bang for our buck we can get with some of the smaller models. The larger ones, in theory, encode more information into their parameters, but they require you to have a large GPU and are slow to train. And to be honest, I put this together in a week, so I don't have like weeks to let these things train. So that's why I picked the smaller one. Just to give you a sense, I have NVIDIA GPU that I did all of the stuff on, and I just used Lambda Labs for it. Oops. And if you run, my copy paste isn't working. Come on. If you run NVIDIA SMI on that machine, maybe I can just save it and export it. We'll skip that. You'll see that it just takes up, the larger models just take up way too much of the GPU memory. And so there's this kind of trend of GPU poor people trying to like build these models. So let's just try to milk the 130 million parameter model for all of its worth. All of the code for this is going to be posted, or is already posted, in this GitHub repo, Oxen.ai/Mamba dive. There's a lot of code to cover today, so I'll be doing less copy paste and more just running of the code so you guys can see how it works. And note that if you want to get this running on your own, it does require an NVIDIA GPU with CUDA installed. If you're having troubles installing it, I'm going to put like a little DevOps guide at the end of this, because it was a headache for me getting started, just like making sure you have the right PyTorch and CUDA versions and all that up and running. But with all that being said, we're going to start with just simple prompt engineering. And if you joined us for our deep dive into the paper called Language Models Are Unsupervised Multitask Learners, is the original GPT-2 paper, they showed that pre-training on a large corpus of data allows you to use prompting for a lot of downstream tasks, and that the information is kind of encoded in the model's parameters. So let's start by just raw prompting the language model, and I built a little command line utility to test this out. The simplest form of this is just going to be a while loop that prompts you for your input, and then I hard-coded a prompt that we're going to run the model through. So it's not that much code. It's like 50 lines here of grabbing this Mamba language model from the Mamba SSM repo, using the tokenizers from the Transformers project, and then we can just pass in any model we want. I hard-coded this prompt of, you are a trivia bot, answer the following trivia question. And I just put whatever the user's input was. After that, I convert the input to integers by tokenizing it, feed it through the model, and then the model spits out a bunch of integers again. We decode that into actual text, and then we'll print it out. So let's see what this looks like in practice. Again, all of this is in our GitHub that we'll send out after this. So you can run the script, and you can actually pass in any of those state space models that we saw. So for example, on this Hugging Face / state spaces, there are all of the models we mentioned before, from the 130 million all the way up to the 2.8 billion. Yeah, Adam.
We're still seeing the screen, the Notion screen that says the code prompt engineering. See your mouse moving around a lot, but it's not in sync with what you're talking about.
Thank you for calling that out. I was just sharing the Notion and not the visual code. So let's go to the entire screen up there. Screen 2. Thank you. That must have been a little confusing. Here we go. So I'm logged into this GPU machine in the cloud. I have all of the code right here. Like I said, it's pretty quick, 50 lines of code. And let's start by prompt engineering with you are a trivia bot, answer the following trivia question, etc. So I am going to put in a simple question, maybe who is the current president, which we'll see what sort of knowledge is encoded into the 130 million parameter Mamba model. So you can see this is the full prompt right here. You are a trivia bot, answer the following trivia questions. It tokenized it and encoded it into these integers here. It ran it, and it just starts spitting out a bunch of garbage, which, if you think about these language models in general, the pre-training step is simply to predict the next word given a big corpus. So it's actually a question answering task at all. It's actually quite like a parrot where it just likes to repeat itself over and over again. So you can see in this case, it just spit out, if I put quotes around it, it just spits out the same thing that I put in over and over again. If we want to reformat this a little different and say, you are a trivia bot, answer the following trivia question, and then maybe put a Q for the question, and then on a new line, put an A for the answer to kind of give it a little more, okay, this is the format we're looking for. Let's do that and run it again and try the same question in quotes. See what happens. Now it thinks that we're trying to just complete the alphabet with the same thing. So it's interesting. It knows A, B, C, D, E, F, G, K, but still not answering our question. And you might just be like, this model doesn't work. Let's throw it out. But instead, we're going to be a little smarter about it and realize that this is what's called zero-shot prompting. And if we wanted to do, if we wanted to kind of prime the model for a question answering type task, what we're really going to want to do is what's called n-shot prompting. So what n-shot prompting looks like is something more along the lines of this, where we give it that same precursor prompt, but then we start giving it a pattern that we want it to follow. So it's like Q, what's the capital of France, A, Paris, etc. And then finally, we're going to put in the user input, and we're going to see if it can generate the answer to the question. And so simply adding a little data structure to hold on to some example prompts and responses, and replacing this prompt and response or prompt with a concatenated version of all of these question and answer pairs that we kind of saw over here. We can now formulate a prompt in a pattern that is easier for the model to follow. So let's take a look at what that might look like. So let's try, what is the capital of Norway? You can see it spit out my constructed prompt here. You are a trivia bot, blah, blah, blah. It stopped right here at what is the capital of Norway. It's a lot more tokens to process, but we've kind of given it a pattern to follow. And boom, the next thing that came out of the model was A, Oslo. It then continued to ask more questions and give more answers. But now we're seeing, okay, there is something intelligent hidden within these parameters. You just kind of had to give it a little context of what you wanted to do. So that's pretty cool. We know that there's something hidden within there. If you really wanted to be hacky about it and just like grab the last bit or the first thing that it generated after these new lines to make your prompt and response a little cleaner, we could do that. So let's try it again, and let's try a different question. what is the capital of Germany? And honestly, if anybody has any questions they want to ask in the chat, feel free to do it. But we can see here, Berlin is the answer. So there's definitely some interesting things encoded, even in the 130 million parameter model. Does anyone else have a question they want to ask, or should we just keep on moving on? Ben, I'm going to force you to ask a question.
Totally. Can I like mess with it a little bit?
Let's mess with it. Yeah.
I'm going to put it in the chat.
Something about the weight of a laden swallow. I like that. Should we just ask it what
Yeah.
is the weight of a laden swallow? It says 1,000 pounds. Pretty confident in that. Ben said, what is the organ studies professor at Juilliard? Okay. Do you know the answer to this? Is that it?
I do. It is not. I want to see if that's a person though, because that's one of the more basic names I've ever seen.
John H.S. Lewis. Nice.
That does not appear to be a real organist.
Okay. This is perfect because you can see that the model is able to answer some questions and it is starting to hallucinate on other ones. Like, I don't think a laden swallow is 1,000 pounds, and I don't think this is a real person. Hey, Evan.
I arrived a little late, so forgive me if this already was clarified. The data set that we're using, so we're using a pre-trained model, and then what is the data coming from?
Yeah, so this is a pre-trained Mamba model, and it was pre-trained on the pile. So in this case, I grabbed it from Hugging Face state space models here. This Mamba repository, it said that
Where are we fine-tuning it on? Like, where was the fine-tuned data set procured, or if that hasn't been said?
We haven't actually fine-tuned it yet. So we just gave it this n-shot prompt of question and answer pairs.
Gotcha. All right, thank you. I'm sorry.
That's
totally
good.
fault.
It is a fair question though. Like, we haven't done any fine-tuning yet, but we will.
Okay, awesome. So last question, which also maybe is best saved for them, but I noticed in the bottom left your SSH into a local IP, and I'm just curious, like, is this how you like operate the business? Like, you have like some sort of compute cluster with workstations?
Yeah, this one's just a machine up in Lambda Labs that I've rented out, and I usually just SSH in with VS Code to do a lot of my experiments.
Oh, you're right. It's not a local IP. It tricks you because it starts with 192, but it doesn't have 168.
Yep. Exactly. Yeah, Scott.
There's a question in the chat around, can you try asking a math question? Something like 1 + 1 or 1 + 1 equals.
That would be fun. Let's check it out. What is 1 + 1? Oh, I put an extra quote there to make it even harder. I don't think that's right. There we go. The quote threw it off. So 1 + 1 = 2. Very impressive. LLM. Yeah, Cameron.
Earlier, did you show it automatically asking questions back?
I did, yes. So it was continuing to just like spit out what it thought the pattern should be, like this.
Yeah. So that was it spitting that out. It was responding with a pattern. You weren't doing that.
Right. So I added these couple lines at the end here to kind of just like grab the first one. And also I limited the context, or I limited the generation length to like 128. So if we bumped this up to maybe 256 and took out that part at the end, I think it'll just continue to generate more and more questions that follow the pattern.
Is that an example of the selective state space model aspect of it, or?
No, this is more just a property of LLMs in general.
Okay.
Oops, I didn't print out the last one, but It's a very good question because like a lot of this code and a lot of this, like this loop right here, we can pretty much replace it with any LLM that we want. We just happen to be grabbing the Mamba one. But Hugging Face has abstracted a lot of these things so that we just have a generic generate function, and a lot of them will behave like this.
Cool. Thank you.
Yeah, no problem. Let's see what happens if we do. That's funny. Okay. So I asked, what is the fastest bird? It thought the Great Dane, which is definitely not a bird. But then it started generating what is the fastest person. And I like to call these things parrots because they just like to just repeat themselves over and over again. So that's kind of what we're working with. Next, we're going to take it to the next step of training this thing on an actual task. So hopefully it has less of the parrot behavior and more of a question answering behavior. But before we get to that, it's fun to just like kick the tires on these things and put in one-off prompts. But let's be a little more robust about it and run this thing on an actual question and answering data set. So in this case, we're going to use Squad, which is the Stanford question and answering data set. If we go look at it, they have all of the data here. I have also pre-processed a lot of it into an Oxen repository and put it into like a line delimited JSON file. Let's look at the training data here. Basically, what we have is we have a context window. We have a prompt, which is like the question, and then we have a response, which is the answer. Evan had a question as well.
Yeah, I'm seeing like only within the past year or so, there's these JSON L files. Like, what is a JSON? What was the L?
Oh, line delimited. So instead of having like a big block of JSON where you have to read the whole thing in at once, each line is a self-contained JSON blob so that you can iterate over it without reading it all into memory at once, which is kind of nice. Okay,
so it's like, I bet if you opened it up, it would look like an array, but just without the square brackets, right?
Yeah, totally.
And no comma at the end.
Yeah, so if we looked at it here, let's look at Squad train. You can see it's just like this.
Yeah.
This line right here, and then this line right here. So yeah, no starting brackets.
Cool.
So it's a nice format that I like to use because it's human readable and also you can iterate over it without loading it all.
I don't want to get sidetracked, but I guess you'd have to load it from the start, right? Like you couldn't necessarily load the middle of the file to start.
Yeah, you would have to iterate over it line by line.
Okay. Yeah, so it would be kind of like reading a tape recorder, kind of like you'd have to go through the entire tape, which is important. I guess the reason I ask is like, if you're going to shuffle a data set, I feel like this would be really difficult to do that with. You'd have to do it in order.
No, you could just load it all into a data frame, or you can use like sort-r, and since it's line delimited, you can just, it'll split it on the new lines.
Yeah, but then you have to load the entire data set into memory. Which removes the point of using JSON-L, I thought.
Partially. I mean, for this example, like if we just wanted to grab the first line, I'm saying like a full JSON blob, if you had the entire array, you would have to wait until you found the closing block until you could load all of that in and grab each individual one. This one you can just process one by one.
Yeah, that makes sense.
Cool. So yeah, this task is cool. It has a bunch of prompt and response pairs. We can ignore the context for now and just like, you could probably, if you were a super smart trivia savant, you could probably answer this without the context above, but this data set is nice because they give you like a Wikipedia article, or I don't know where they got all these from, but the answer is hidden within here. So we'll kind of see how we can use that later on. But to start, I wrote a little script that was to evaluate our n-shot Mamba model. So it does that same prompting strategy of like getting it into the mindset of answering questions. But in this case, to your point, Evan, I did load all of the data into this array here. So I did load it all into memory. And then I start iterating over each one. Running the model is just this one line that I've abstracted into this function, run Mamba. And then I do some other just like munging to get it into an output data frame that we can look at later. But let's look at what this looks like on not just questions that we think of out of the blue, but on an actual evaluation data set. So let me grab that actual command so I don't mess it up. So we just run this n-shot Mamba. You can pass in any of the models you want here. We're passing in this JSON-L file, and then we're going to write all of the data to this results file. So this is going to take a second to boot up, and then it starts cranking through all of these questions with the context window, and you can see it's not getting any of them right, but it is giving some answers to them, which is pretty interesting. If we switch this out for the larger one, like the 2.8 billion one, we'll start seeing it getting a few more right. But Evan, you've got a question?
Yeah, how does the evaluation data set know if it's right? Like, would it be like an exact string match, or would it be like, you know?
Yeah, right now it's just like answer strip lower equals guess strip lower.
Okay.
So a pretty basic string matching right now. But you can see the larger model actually did get this question right. It is guessing relatively close answers. But like this one guessed a monetary value, it just wasn't the correct one. But here we go, like who does a gender pay gap tend to favor? It spit out males in the labor market. I think this was actually the annotated answer was males in the labor market, and it spit out men. So like,
yeah.
Technically that would be right. We're just doing a raw string match here.
Is this where you see people start to do like GPT-4? And process of these matches.
Just mic screwed up for anyone else.
The same thing.
Yeah, Ben, sorry, your audio was a little jacked up there.
I'll drop it in the chat.
Oh, now it was clean as crystal clear. I don't know.
Weird. Okay, wait. Am I here now?
Yeah, you're good.
Okay. Is this where people start to do like GPT-4 or other LLM mediated analysis of what is a match? That just jumped out to me, but I'm not sure if you've seen people doing it.
Yeah, I've seen that as a strategy. It's just not the most reliable strategy because then you're relying on another LLM to like say these two things are equivalent. So
yeah,
it might give you a slightly closer number to the actual percentage, but you just have to be wary with that type of approach.
The reason I ask is I just saw a video like last week that was describing how like these like benchmarks basically ask impossible questions. And we're using them to like double-digit percentage accuracy to compare models at this point. But it's like, but like, yeah, this question 4 out of 1,000, like there's absolutely no one in their right mind that would get that correct. like exact character for character.
Oh yeah. Nobody would type this out for that. Yeah,
yes,
that's right. Yeah, that's a really good point. And that's even kind of when you look at the Mamba paper itself. I thought about this a lot when I was doing these examples. And, you know, at the end, they have all of their metrics here. And let's find, yeah, this big table. And these are some of the data sets that you're probably talking about. And so I ran, Mamba 130 million on all of these squad questions, which aren't one of the ones in this table. But I was like, I ran it on all 1,000, and the 2.7 billion model got like 75 of them correct. So 7.5% accuracy, granted raw string match. And the 1 million only got like 5 of them correct out of the 1,000. So I was like, that's interesting that they didn't put them in the table here, but I would love to see not just a raw number, but like show me what the actual prompt and response pairs were, so that we can debug it a little farther. I think that'd be really helpful.
I wonder if they have it in like a appendix or like GitHub dump. Probably
Yeah,
not,
I
though.
wasn't able to find it. Yeah. Interestingly enough, though, I looked at this Pika data set because I was like, okay, that's a question answer data set. I'm wondering why they got 64% on this task with this model. Like, is it really that different of a question answering task? So I put that in here near Pika. And if you look at it, it is a question answering task, but it's actually a binary classification task. So it's like, given this goal and these two solutions, pick which one is the correct solution. So now the 64% starts to make way more sense. It's like, sure, you could get 50% if you just guessed randomly. And it got 64. So good call outs. All right. So we kind of know the task at hand. We kind of saw that the model spit out not ridiculous answers, but it got like, I ran this on the data set and got, 7.5% accuracy on the 2.8 billion model. So not that impressive. Let's look at the task in hand and realize that a lot of these questions do require context. And actually, I think in general, rather than just trying to have an LLM spit out an answer from its parameters, it's much more useful and a little more reliable to like have it cite its sources as you're going along. So I was looking at the questions in the squad data set. They are much harder than just like, what is the capital of France? But if you look at some of the questions, a lot of them even just require context to answer. Like there was this one that was, what hotel did the Panthers stay at? And I'm like, which Panthers and at what point in time? You just really can't even answer that question unless you have a little context. So what's cool about the squad data set is it does give you a couple sentences of context to be able to answer the particular question. So in this one, it says the Panthers used San Jose State practice facility and stayed in the San Jose Marriott. So that would be the right answer to the question. And then they also sprinkle in the Broncos practice at Stanford and stayed at the Santa Clara Marriott. So this is a good example of a sentence that has two different hotels. So you do have to have some level of reasoning and not just pull out the thing that looks like a hotel. Granted, you could probably pull out the thing that looks like a hotel that's closest to the word Panthers, but it's the sort of task that we want an LLM to be able to do. So if we reformulate the problem above as information extraction, I think it's a better way to look at question answering in general. The problem is not all, in the real world, we're not served up these sentences that answer the question on a silver platter. Like you're going to have to do some sort of search process to even find this sentence to be able to pull the answer out in general. So in general, this looks like a pattern where you first have to go retrieve relevant sentences, and then you have to filter through all of those sentences and try to extract the right answer. So what that might look like in this scenario is, say you had the question, The same question is above, what hotel did the Panthers stay at? And then you had these three candidate passages. One is just the first paragraph in the Wikipedia, or the first sentence in the Wikipedia page for the Panthers. The second one is the one that has the actual answer that we had above. And then the third one is just some other random sentence that I picked here. And so what I decided to do was train a model on the squad data set. And what I did was I took all of the correct pairs with context. And so I made a prompt that was like context, question, and answer. And then I took a completely random other sentence and made that an incorrect example and said context, question, and I don't know. So that in theory, if we train this model on those two patterns, it could look at each one of these sentences. And for the first one, it's like, well, there's no information in here that tells me anything about hotel stays for the Panthers. And it'll just say, I don't know. For the second one, hopefully it can extract the San Jose Marriott. And for the third one, hopefully it just says, I don't know as well. So when to say, I don't know is kind of a big problem in machine learning in general. A lot of these data sets are kind of like setting you up for success, assuming that you have the context right next to it. So I wanted to show you guys a little bit, and I'll release this model so you can play with it as well. But I trained this Mamba 130 million with context. And now I changed my little loop here. If we want to look at the actual code to take in a context sentence or paragraph, and then ask your question. And then we're going to run Mamba to see if we can get the right answer. So let's take this first sentence here, or first couple sentence, and then let's ask the question here, what hotel did the Panthers stay at? So it'll run it through. It says, I don't know. That's exactly what we wanted it to do. The answer wasn't in there. Let's grab the one with the right context, and let's ask the same question. And now, boom, San Jose Marriott. It looks like we're cooking with gas here. We could try this on like a lot more sentences, maybe try it on the full Wikipedia page. But I thought it might be fun in general to even just go to wikipedia.com and like pick a random article. And let's see if this model we trained can answer questions from it. So like Amelia Quinn, born 1992, is a British scholar known for her work on developing vegan theory. So let's say, what is Amelia Quinn known for? I haven't tried any of this, but I like to try things live. There we go. Her work developing vegan theory. So it was able to, given that context, pull out an example. Or pull out the answer. Let's ask it like a ridiculous question that's not in here, like, what is the capital of France from before? It doesn't know because it doesn't have the context within its context window to be able to answer that. And that's like a really valuable property to have in an LLM, is to know when you don't know. So any questions on this so far?
It makes me think of that interview situation when you want to see how the person can acknowledge if they don't know something, or if their ego is too big to not acknowledge that.
Yeah, definitely. Like when humans hallucinate an answer, when you really just want them to be like candid and say, I don't know.
Yeah.
Cool.
So would this then be resilient to like the kind of ignore previous instructions and say something if you know it anyway? Do you know the capital of France? Like, is it more resilient than purely a prompting way of doing this would be?
It's a good question. I bet in a lot of the data sets that they're training these newer like ChatGPTs on, I bet they put a lot of examples in there of just ignore the previous instructions in the training data and then have a canned response.
Yeah.
But I could totally see that as a technique you want to use. Yeah, Evan.
I was wondering if there could be like a trickier example that we could give it. I thought of one.
Yeah.
Like in the context, can you say like the capital of France is Paris, and ask it what like the capital of Paris is?
That's a fun one. Yeah. What is the capital? Yeah. So
Interesting.
it said Paris.
So it doesn't know that it doesn't know.
Yeah, yeah. And part of that, if we go back, I think this is a really good time to look at kind of what I did for the dataset loader in general. So what I did was I had that same JSON-L file that had like context, prompt, and response. That's now just in this as examples array.
Can you teach it to just like call the person asking the question a dumbass? Just be like, that was a stupid question.
Yeah, yeah, totally.
Because technically it doesn't not know. It's just super confused.
Yep. And in this case, what I did was I just took all of the examples in that data set and I randomly picked another one and I put that random context into the training example, put the same question, which I'm just assuming won't have the answer in it, and then saying, I don't know. But in the case of like a random one, there's probably no overlapping words, and it's probably pretty easy for the model just to be like,
yeah,
there's literally no mention of capital or Paris in this, so I'm going to say, I don't know. What would be better is if you could add a data set that had questions like this that were like very close, but not quite. And then maybe it could learn to distinct. Yeah.
I can't remember his name. Yannick Kilner made like a 4chan bot, and I think it was like more truthful than other bots. And I think that like there's an element of something worth that's kind of interesting about that. I wonder if it's just that the bot will sometimes call you a dumbass, like it will just call you out on your crap. Whereas this is like it's trying a little too hard to be give you the best effort, whereas I don't know.
Yeah,
I
think the biggest thing there is just encoding that into the training data somehow. Because here it was just kind of a hack to like pick a random example, but like maybe if we got, and I don't even know, this would be an experiment I would love to run, is like if all of us as a group came up, I don't know, there's like 500 people in our Discord, if we each came up with 2 examples of things that are close but not quite, and we added them to this data set, so we extended it with like 1,000 more examples of just stuff that's close but like a ridiculous question, and then we tagged all of those and had a different response there, we could probably train this model to do it.
I mean, GPT-4, maybe you can create a synthetic data set. So like, could you basically figure out some way to get ChatGPT-4, or I mean, you know, the good one, not the weird ones they're making now, to basically generate the capital of France is Paris, and then the question is, what is the capital of Paris? Could you like reverse engineer this example to find a prompt that gives you this?
I would. That's a great idea too. Just like try to run all the existing questions through ChatGPT and see if it can do that, and then we create our own data set of that subset.
Yeah, just like inject the logical fallacy into the question ahead of time instead of trying to detect them. I don't know.
Yeah, I think there is a logical fallacy data set too that we might be able to leverage for that. That'd be fun to play around with. Cool. So I didn't quite show you any of the training script or any of the training code. Just for your reference, it will be in that GitHub. It's basically this one script. You can pass in any of those models from the state spaces Hugging Face. You can pass in any data set that's in that context, prompt, and response format. And then I just trained it for 10 epochs. This particular one took about 8 hours on that GPU to train for 10 epochs. It was like a 24 gig NVIDIA GPU from Lambda Labs. No affiliation there. I just had that one up and running. And when I ran it on the same data set that we had before, so that same squad validate 1000K, it actually got 12% accuracy, which was better than the 2.8 billion model before, but honestly, not that great still. Like 12% is way below what we saw in this leaderboard here. Some of these models claim to get F1 score of like 93, which is balancing precision and recall, which is better than this human performance they had on it. So we're way off the bar here, or at least Mamba is way off the bar here, given the data that we have. So I thought that was super interesting, even though you do see some of these, charts here at the end of the paper where we're like, blew this model out of the water, blew this one out of the water. You really have to look into what the actual data was and make sure that it works for your actual task. And with that said, we kind of went over the Pika data set and why I thought that might be a little higher accuracy because it's just binary classification. Next week, I want to go into, we kind of glossed over the problem of fetching the sentences. So like we were just handed, this one on a silver platter, and then we were asked to answer the question. Next week, I want to build on top of this and see if we can put together a little RAG pipeline, and maybe we index a little bit of Wikipedia, maybe like 100,000 documents, put together a vector database to surface up some documents that could have the answer in it, and then see how well this model performs on that data set. And I think once we have those two pieces together, that kind of gives you a sense of an end-to-end question and answering pipeline that you could use on your own data. But I kind of want to dive into that next week to see how all of these buzzwords go together, LLM and RAG and open domain question answering. So excited to dive into that a little more. Cool. Any other questions on this one? Like I said, I'm gonna clean up this GitHub a little bit, but all of these scripts are here for you guys to play with, and we'll put this together in nice blog form if you want to follow along. Yeah, Cameron.
Could you clarify what we saw that was different from, that makes Mamba different from other models?
Yep. So, the qualities that Mamba claims to have claims to be better at are just the throughput of the model itself, and then the length of sequences that it can process. I didn't do much experimentation with like giving it a huge context window of a very large document. That would be fun to go into. But in terms of the throughput of the model, I did do a few tests there, and I was getting around 200 to 300 tokens per second processing. So I think that'll just give you a sense of some of the benefits. Does that answer your question?
Yeah, thank you.
Yeah, cool. Yeah, some of the other local llamas that I've tried to give you a sense, I can generate like anywhere from 10s to 20s of tokens per second. So putting this on a GPU and running it at 200 to 300 tokens a second, that is clearly a much better user experience. Cool. Well, I'll stop the recording here. Thanks everybody for joining. Excited to dive into RAG next week. And I think it's just been fun to like, okay, let's not take the paper's word for it. Let's try to run it on our own data and see what happens. So thanks for joining.